So today, we're going to start learning about our gas laws. The first thing we'll do is review kinetic molecular theory. So the first couple slides, don't write anything down. We're just going to review them, and then I'll let you know when I want you to start writing. So first, let's just review some of those key pieces of kinetic molecular theory. So the first one is the size of gas particles are tiny, and the space between gas particles is really large. So we say that the size of the gas particle is negligible compared to the space between them. What does negligible mean? Have you heard that word before? Okay. If you were to take one piece of hair from your head and you were to pull it out, would you look any different? No, right? Because that one piece, it's negligible compared to the rest of the hair on your head. So negligible is it's so small it doesn't matter. Okay. We also know gas molecules are in constant random motion. Okay. They do end up colliding with other objects, so either other gas particles or the walls of their container. We call those collisions elastic, which just means they hit and bounce off. And when that happens, they don't gain or lose any kinetic energy in the process. Different gases have different kinetic energies. And then finally, temperature increase is directly proportional to kinetic energy. So by directly proportional, it means if you were to double the temp, you double the kinetic energy. Okay. So then this week, we've also looked at, what happens if we add or remove a gas? Okay. So if you add a gas, you add more particles to the container. That ends up increasing the pressure, but why? Okay, more collisions. So remember, what causes pressure? Collisions. So if you have more particles, more collisions. If you take gas out of the container, pressure goes down. Why? Good. Less collisions. Less particles in there, less collisions with the wall. And then in general, gases will just move from high pressure to low pressure. Okay. So a pop can. What happens when you open a pop can? What kind of sound does it make? Okay, good. Everyone mimic the sound. Okay, what is that sound? Carbonation, which is gases, right? So before you open that pop can, what's the pressure inside the pop can? High relative to outside, right? So when you open it, where does all that gas want to go? Out. Okay, so gases move from high to low. Okay, and then finally, we also talked about changing the size of the container. I think you looked at this one when we did the FET simulation earlier. So if you reduce the volume, you make your container smaller, pressure goes up, but why? What causes pressure? Collision. So if the container's smaller, what happens more? More collisions. If you increase the volume, so you make your container bigger, what happens to your number of collisions? Less. So what happens to your pressure? Less. Good. Okay, so does that kind of sound like a nice summary of what we've learned this week? Okay, so far, those have been qualitative though, right? We've just been doing increase or decrease. So now we're going to start learning about how do we actually know the actual pressure or the actual temperature or the actual volume. So we're going to use gas laws for that. We'll learn two today. The first one is called Boyles' law. So you need to make sure you get the title. And then you just need the bold. Okay, you don't need the formal definition. We'll talk about the formal. But you just need the bold words in the equation in your notes. So Boyles' law is for a given mass of a gas at constant temperature. The volume of a gas varies inversely with pressure. Now, how many of you hear that and you're I'm not quite sure what that means because it's a lot of jargon. Okay. So if you want to simplify it, you can just write what's in bold. So if you increase the volume of a container, you decrease the pressure. Okay. Or if you decrease the volume, you increase the pressure. If you're more of a visual person, you could even do arrows. So if you increase volume, you decrease pressure. So you can simplify this to whatever makes most sense to you. And then finally, you need to get the equation for Boyles' law down. Okay, so everyone write down Boyles' law. Okay, so P1 V1 is equal to P2 V2. What do you think the P stands for? Okay, P stands for pressure. And what do you think the 1 subscript means? Okay, P1 means the first pressure or the initial pressure. And then what do you think the V stands for? Okay, volume. Again, the V1 stands for initial volume. Okay, P2, still pressure, is just final pressure. And then V2 is final volume. Okay. So you definitely need the equation down in your notes. Okay. If you aren't quite sure what like the P1, V1, P2, or V2 mean, go ahead and write down the key. If you know P1, V1, P2, V2, do you need to rewrite the key? No. Okay. When we use Boyles' law, we're going to use units of pressure. And I think units of pressure are unfamiliar pretty much to this point, because have you ever like measured pressure very often? Okay, so in your notes, I want you to write down some units of pressure, and we're going to write conversions because we'll have to convert between them. If you see my whiteboard, I'm just going to copy that. So one common unit of pressure is atmospheres. Okay, so ATM is an atmosphere. And we're going to just write conversions. Okay, so 1 atmosphere is equivalent to 760 millimeters of mercury. That's also equivalent to 760 torrs. And that's equivalent to 101.3 kilopascals. We don't use PSI because what does the PSI stand for? Okay, say that again. Yeah, I think it's pounds. Isn't it pounds per square inch? The keyword there is inch. What unit do we not like in science? Inch. So you're not going to see PSI in here. Okay, so I think for most of you, these 4 units are probably pretty unfamiliar, correct? Okay, so we need to get used to them, and we will with time. Okay, so like the more we see them, the more we'll get used to them. ATM is atmosphere. mmHg is millimeters of mercury. Okay. Torr is torr. And then kPa is a kilopascal. So we just have to start, like when you see these in problems, if you see the unit, we need to start thinking like, okay, that's telling me the pressure of something. And then you'll have to convert between units sometimes. Like you might have to get from like atmospheres to millimeters of mercury. Okay. Can you use this to convert? Okay. Let's just do a quick practice problem. Let's say we have 0.95 atmospheres. And we want to know what that is. Let's say we want to convert it to torrs. Okay. We can just do like a really simple dimensional analysis problem. Okay, so 0.95 atmospheres is our starting box. And then we just use that conversion. So for every 1 atmosphere, how many torrs does that equal? Okay, do you see how 1 atmosphere is equal to 760? Yeah. So if you want to convert between like atmospheres and torrs, you just multiply it. Okay, so you just take 0.95 multiplied by 760. And that's how you could convert it into torrs. You with me? Good. Okay, if you want to go from torrs to atmospheres, instead of multiplying, what would you do? Divide. Just divide. Okay, do you think you could do some of those on your own? Yeah. Perfect. Okay, we're going to do a practice problem. Are you okay if I change this slide? Yeah. Okay, I know this one is easy. They're not always like this easy, so like go with me on their process. Okay. So if you have a gas at 1 atmosphere and the volume changes from 5 mils to 10 mils, what will be the new pressure? Okay, I know some of you already like have this number in your head, like you've got it. But we're going to start small. Eventually we get to the point where you have like 5 different equations, so like follow the process with me. So the first thing you need to do is just identify what's given to you in the equation. So I typically just start at the beginning and I underline the numbers. Okay, so the first number is 1 atmosphere. What is an atmosphere telling you? Okay, that's telling you the pressure. So P1 is 1 atmosphere. Then I'm just going to keep reading the word problem till I get to the next number. Okay. So the next number is 5 milliliters. What's a milliliter telling you? Volume. Okay. So V1 is 5 milliliters. Okay. Then I'm going to keep going. That third number is 10 milliliters. What's that giving you? Milliliter is volume. Okay. And it's the second one, so that's V2. And then what are you solving for? P2. Okay, P2. Okay, so always start here. Like, we're eventually going to get to the point where you have 5 different equations, and you're going to have to figure out, like, which equation you use. So this is how you'll figure out which equation you use.
Hello. They haven't gotten you.
Okay. So now, what equation do we know that has P1, V1, P2, and P2 and V2 in it? Okay, it's Boyles' law. So we're going to use Boyles' law. So P1, V1 equals P2, V2. So from here, we just plug in. So 1 atmosphere times 5 milliliters is equal to P2 times 10 milliliters. Okay. What's 1 times 5?
5.
Okay, 5 is equal to P2 times 10. What do I do to get P2 by itself? Okay, divide both sides by 10. So what does P2 equal? What's 5 divided by 10?
1/2.
Good, 1/2, 0.5. What's our unit for pressure? Okay, it's gonna match your initial unit, so it'll be atmospheres. Okay, this time we have a balloon that contains 30 liters of helium gas at 100 kPa. What is the volume when the balloon rises to an altitude where the pressure is only 25 kPa? So we're going to start by just identifying the variables. So start at the beginning of the word problem. Do this with me. Okay, and I just start with the first number. So the first number is 30 liters. So what is that? Okay, volume. So V1 is 30 liters. Okay. What's the next number given? Okay, 100 kPa. When you see kPa, what unit are you thinking? Or like what kind of measurement are you thinking? Okay, kPa is pressure.
What's V?
Volume.
I just had to make sure. I know someone else was wondering that in this class. I know it wasn't just me.
Okay, what's the third number given?
Maybe.
What's that next number?
25.
Okay, 25, and it's kPa. So again, what kind of measurement is that? Okay, that's the second one, so it's going to be P2. And then what are you solving for?
Volume.
Okay, you're solving for that second volume. Okay, so then you have to look at what equation do you know that has V1 and P1 and V2 and P2 in it? Okay. So what equation do we know that has those 4 variables in it? What's the name? Good. We know Boyles' law. Okay, so we're going to use Boyles' law. So P1 V1 equals P2 V2. Can we just plug in our numbers and calculate it? Good. Okay, what's 100 times 30? Okay, so we have 3,000 equals 25 times V2. What's my next step? Next step, you got to divide both sides by 25. Okay. What's 30,000 divided by 25? Okay, 120. And what's your unit for volume? Okay, liters. It'll just match whatever V1 was. Okay, questions so far? We're okay. Okay, units for Boyle's law. They don't matter for this one, okay? So for volume, what are like common volume units we're used to? Liters or milliliters, okay? So for volume, it doesn't matter if you're in liters or milliliters. The only key is they have to be the same. If like your initials in liters, what does your final have to be in? Liters. You just can't, one can't be in liters, one can't be in milliliters. And then for pressure, you can use any of the 4 pressure units we talked about. So pressures can be in atmospheres, millimeters of mercury, torrs or kilopascals. The only thing is, if P1 is in torrs, can P2 be in kilopascals? Okay, no, what do you have to do? You have to convert them so they're the same unit. It doesn't matter which way you go. Okay, like they could both be torrs, they could both be kilopascals. They just have to match. Does that make sense? Okay. So now we're going to shift gears. You don't have to write this down because I think you already know this one. But we are going to look at, well, how does temperature affect a gas? So if you increase the temperature of a gas, what happens to it? Okay, pressure goes up. Those particles move faster. What happens to those number of collisions? Okay, they increase. If you cool the gas down, what happens? What happens to the number of collisions if you cool it down? Okay, they decrease, so pressure decreases. So now we're going to look at how does temperature and volume relate. So that brings us to our second law, which is Charles's law. Okay, so get down Charles's law. And again, you just need the bold. You don't need like the formal definition, but you need to have the bold stuff written down. Okay, so Charles's law says the volume of a fixed mass of gas is directly proportional to its Kelvin temperature as long as pressure is constant. Okay, so what that means in simplified terms, if you increase the temp, you increase the volume. Okay, if you decrease the temp, you decrease the volume. And hopefully you can remember one of the stations on Wednesday. Do you all remember when you took that balloon and you put it in the cold beaker and the hot beaker? Okay, was that one like a really good example of as you heated it, the volume definitely got bigger, and as you cooled it, the volume got smaller? Okay, and so the equation for Charles's law is V1 over T1 is equal to V2 over T2. Okay, you definitely need to write that down. What do you think V1 stands for?
Volume 1.
Okay, so V is still volume. 1 is initial. What's the 2 talking about? Final. Okay. What's T talking about? Okay. T equals temp. This time, the unit for temperature matters. Okay. Temp has to be in kelvins. Okay. So, when you write your equation, write yourself a little note. Temp has to be in Kelvin. Okay, so temperature units have to be Kelvin. Always, always, always. So you have to know how to convert to Kelvin. Okay, so you need to get this equation down. Okay, Kelvin is just whatever degrees you are in Celsius plus 273.
Physicist Lord Kelvin.
Okay. Okay, so remember plus 273. So that's how you get to kelvins. Let's talk about why. Why Kelvin? I'm going to rewrite Charles's law. Okay, what's special about the Kelvin scale?
I don't know.
What's the lowest number you can get? Okay, absolute 0. Is there any negative numbers on the Kelvin scale? Okay, look at our equation for Charles's law. Temperatures in the denominator. Can you get negative in Celsius and Fahrenheit?
Yeah.
Yes, however, can you divide by a negative number?
No.
Okay, so therefore, does Charles's law work if you had a negative number in the denominator?
No.
Okay, so you have to be in Kelvin. we have to have a positive number in the denominator. You with me? Okay. It wouldn't. Okay, we're going to do one practice problem for Charles's law. So we have a balloon inflated in an air-conditioned room at 27 degrees Celsius, and it has a volume of 4 liters. The balloon is then heated to a temp of 57 degrees Celsius. What's the new volume if pressure remains constant? So what's the first thing you should do? Before you convert, we got to identify. Okay, identify what's given to you. So what's the first number given to you? Okay, T1. Okay, it's 27 degrees Celsius. Are you ever going to use Celsius in the gas law unit? Never, ever, so let's just immediately convert it. How do we convert it? Okay, you're going to add, I'm going to choose it, 273 to it. So what's 27 plus 273? Okay, 300 Kelvin. Okay, so if I were you, I would just immediately convert my temps to Kelvin so you don't forget. Okay. Let's talk sig figs for a second. When's the last time we've added with sig figs? It's been a while, but it's going to change our answer a lot. When you add with sig figs, it's just whatever the one with like the least number of decimals has. So 273 doesn't have any decimals. Okay. 300 doesn't have any. However, those zeros are significant. So you just got to put a dot decimal there. Okay. It just needs to be 3 sig figs with that 300 instead of 1. Or else you're going to round crazy. Okay. All right, what's the second number given to you? 4 liters. A liter is a unit for. Okay, so V1 is 4.0 liters. Okay. What's the third number given? Okay. So T2 is 57 degrees Celsius. Are you ever going to use Celsius? Okay, so what are you going to immediately do? Okay. Add 273 to that. Okay. Are you getting 330?
Yeah.
Okay. You need all 3 of those to be significant, so just 330 in a decimal. Okay. And then finally, what are you solving for? Okay, V2. So start here. Okay, I know today I told you we're using Charles's law. However, we're going to get to the point where there's 5 different equations you can use. So this is what you do so you know which equation actually works. Okay, so you write down your variables, and then you have to look, well, what equation matches up with T1, V1, T2, and V2? And what's the name of the equation? Okay, this one is Charles's law. I'm going to scoot this up. Okay, so Charles's law. V1 over T1 is equal to V2 over T2. Okay. So now I'm just going to substitute in my numbers. So V1 is 4.0 liters. T1 is 300 Kelvin. V2, we don't know. T2 is 330. I don't know why I have parentheses. I don't think they're important. Okay, now how many of you kind of hate algebra and you're looking at this equation and you're like, I really don't want to solve it? Okay, here's the good news. You don't have to use algebra to solve this one. You can just cross multiply. Okay, so watch up here. So if you're someone and you're like, I hate algebra, I don't really want to solve for V2, you watch. We're going to cross multiply. You're going to start in the diagonal where your variable is not in. Okay, so you're going to start on this diagonal, the one that has 2 numbers. I'm going to circle it. Okay, so multiply those 2 numbers. So what's 4.0 times 330? Okay, are you getting 1,320? Then all you have to do is divide by the diagonal with the V2 in it. Okay, so take that number, divide it by 300. Okay, so what are you getting for V2? Okay, 4.4, and what's your unit? Liters. Good. Okay, so for you algebra lovers out there, you love doing algebra and you want to like move your variables to both sides and divide, can you do algebra? Yes, you go for it. For those of you who don't love algebra, what method are you going to use to solve these ones? Cross multiplication. Okay. All right, finally, just double check, does your number make sense? Okay. Look at your temperatures. Temps went from 300 to 330. So what would you expect your volume to do? Increase. A lot or a little? Just a little. Okay. And so you went from 4 to 4.4. Does that number seem reasonable? Okay. So always like pause at the end and make sure your number makes sense.